All right, so today we'll be discussing properties of limits. The first thing on our list, things to do, is we're going to prove that limits are unique. Then I'm going to introduce left and right-handed limits, something we haven't talked about yet. We'll see a useful theorem about these limits. And lastly, we'll discuss how to prove that a function is continuous on a closed interval. Turns out you need left and right-handed limits to do that. That's also something we haven't discussed yet. So we're going to get all that over with today. All right? So the first thing on our list, the limit uniqueness theorem, we're going to show that if the limit as x approaches a of f of x exists and equals some value L, then that value L is unique, meaning there can't be two different numbers here satisfying this statement. Okay? That's very useful information. A function can't approach two different limits at the same time. We're going to show that the epsilon delta definition that we have developed and have been working with actually forces the limits to be unique. Okay? So let's go through the proof. The standard way to prove that something is unique in mathematics is to assume that it's not unique. Okay? So we're going to go by way of contradiction. By way of contradiction, we're going to assume that we also have a different value here, m, satisfying this statement. So by way of contradiction, suppose that the limit as x approaches a of f of x equals L, and also the limit as x approaches a of f of x equals m, where m is different than L, where m is not equal to L. Okay? So that's what we're supposing. And now we're going to show that some sort of contradiction will come up. Okay? That's the point. So let's first write out our definitions. Okay? We're assuming this is the case. We're also assuming that this is the case. So we know what these things mean, right? We can write out the formal epsilon delta definitions for each of them. So let's do that. So the limit as x approaches a of f of x equals L, what that means is for all epsilon greater than 0, there exists a delta greater than 0. Now I'm going to call this delta 1 because there will be another delta coming into the picture when we write down this definition. Okay. So for all epsilon greater than 0, there exists a delta 1 greater than 0, such that 0 less than x minus a less than delta 1 implies f of x minus L is less than epsilon. Okay? Very familiar. What about the other one? Limit as x approaches a, f of x equals m. That implies that, again, for all epsilon greater than 0, this time there exists a delta 2 greater than 0, okay? Possibly a different delta than this, such that the same implication, 0 less than x minus a less than delta 2, implies f of x minus m this time can be made less than epsilon. All right? So we're supposing this, so we're supposing all of this. Okay? Now let's take a look at what we have here. For all epsilon, there exists a delta 1, such that if x is chosen within a delta 1 window around a, then f of x is pretty close to L. It's within the epsilon band around L. Okay? Here we're told that there exists a delta 2, such that for all x is within the delta 2 window, f of x is within the epsilon band around m. Okay? Now, these are possibly different deltas, but it turns out that there exists a single delta, such that if 0 is less than x minus a is less than that single delta, then both of these statements hold at the same time. What is that single delta? Well, it's the smaller of the two of these. So we can fold these two statements into one like this. We know that for all epsilon, so what do we know? For all epsilon greater than 0, there exists a delta greater than 0, a single delta, such that 0 less than x minus a is less than that single delta implies f of x minus L is less than epsilon, and also f of x minus m is less than epsilon. Okay? And by the way, this single delta is the smaller of these two deltas over here. It's the minimum of delta 1 and delta 2. Okay? If you remember, if a particular delta holds in this implication, any smaller delta will also hold. Okay? Because that will just be a subset for a smaller delta of this original thing, which happens to work. Okay? So this is the statement that we know and we're now going to use. Okay? And we're going to show that some sort of contradiction will come out of this. Okay? We can't have, for all epsilon, there exists a single delta such that for all x's in here, we have both f of x super close to L and also f of x super close to m at the same time. This is the statement which will lead to our contradiction that we're looking for. Let's maybe draw a graph to visualize this, get some intuition going. So on a graph, let's suppose that A is over here, and we have L and M. Now, I'm going to put L as less than M. It could have been the other way around, we don't know. But we at least know that the two aren't equal, okay? That's our supposition. So, without loss of generality, we may assume that M is larger than L. Maybe I should write that down here, okay? Without loss of generality, that's the abbreviation that mathematicians use to conserve energy, assume that M is larger than L. There we go. Okay? So what's happening on our graph? We know that no matter how small our epsilon band is, there always is a little delta window here. Around A, there's A plus delta, there's A minus delta, okay? Such that whenever we take an x from here and feed it into our function will both be around an epsilon band around L, within an epsilon band around L, and also within an epsilon band around M. Now, we know that this is true for all epsilon. So what we could do is choose an epsilon that's so small that the two bands will not intersect. Okay? So we're going to choose an epsilon such that when we put down our epsilon band around L, okay, there's our epsilon band around L, and also our epsilon band around M, okay, there it is right there, it's going to turn out that these bands are completely disjoint. And then we're going to have a problem, because our statement says that f of x is both within the first band and the second band for any x within this interval. Now f is supposed to be a function. It can't be both here and here at these different x's. Okay? That is where our contradiction is going to come from. Okay? The height of this band over here is L plus epsilon. Okay? So on the one hand, our function is going to have to be smaller than L plus epsilon. That's what that's telling us. On the other hand, f of x is going to have to be larger than m minus epsilon, the lowest that it can be and still be within this band. Okay? Now all we have to do is choose our epsilon such that m minus epsilon is going to be larger than L plus epsilon. That's another way of saying that the bands will be disjoint. And then we'll get our contradiction from the fact that f has to be smaller than this, L plus epsilon. L plus epsilon will be smaller than the m minus epsilon, or perhaps equal to it. And then f of x will also have to be larger than the m minus epsilon. So we'll get f of x being larger than f of x, which will be a contradiction. Okay, so we're going to pick a specific epsilon now. Pick epsilon equals something, okay? And now we know that there's going to be a delta such that both of these things are going to hold, okay? Pick epsilon equals something. Let's just leave that blank for now. We know there exists delta such that 0 less than x minus a less than delta implies the following, okay? It implies that f of x minus L is less than epsilon, and also that f of x minus m is less than epsilon. So the first statement tells us, as we've already seen with the graph, that f of x is definitely less than L plus epsilon. So this tells us that f of x is less than L plus epsilon. Okay? This statement tells us that f is larger than m minus epsilon. M minus epsilon is less than f of x. And now all we have to do to get our contradiction is choose epsilon to be, let's look at the graph over here. What is epsilon here? It looks like about a third of the distance between m and L, right? So we know that if we choose that for our value of epsilon, then we'll get that the L plus epsilon, or rather, yeah, the L plus epsilon is going to be less than the m minus epsilon. And by combining these two statements, we'll conclude that f of x is less than f of x, which will be the contradiction we're looking for. Okay? So let's pick epsilon to be what it appears to be on the graph here. M minus L, the distance between m and L, divided by 3. Okay? We know that that's going to work. So pick epsilon to be m minus L over 3. Okay? And then what do we know? Well, combining these two inequalities, let's combine them both down here, we know that f of x is going to be less than L plus epsilon, which by the way is equal to L plus m minus epsilon, or m minus L rather, over 3, okay, for a particular value of epsilon. And now we can say that this is less than, it's definitely less than, L plus 2 m minus L over 3. Okay, so graphically what did we do? This upper limit on the band here around L was our L plus epsilon, which is our L plus m minus L over 3. Now if we add another third, we get up to this band over here, okay? So that's why we multiplied this through by 2. We added just another epsilon distance over here, and now from the graph we see that this quantity here should be equal to m minus the epsilon, m minus L over 3, okay? So we have that this is less than this, okay? And now this should simplify to m minus L over 3. Let's see if it does. We have L minus 2/3 L, so there's going to be a third L left over, and then we're going to have 2/3 m. And now if we mess around with this a little bit, we get that this is m, and now we have to subtract m over 3, okay? And then add L over 3, right? We just wrote the 2/3 m as m minus m over 3. And now this is equal to m minus m minus L over 3. You see that? I just put these things under a common denominator and the negative pops in there, okay? And this is exactly m minus epsilon. Perfect, so our intuition was good here. M minus epsilon, and that's less than f of x by the second statement. So f of x is less than blah, which is equal to blah, which is less than a different blah, which is less than f of x. So f of x is less than f of x for all the x's within this window. This window has strictly positive size, and our conclusion is that this can't happen. F of x is supposed to be a function. We've reached the contradiction. So, oops, contradiction, exclamation point. We cannot have the function approaching two different limits, okay? We assumed this, we wrote out our definitions, we combined the two definitions, we did some algebra, we picked a specific epsilon using the suppositions we made, and we showed that there's a contradiction. Wherein lies the problem? In our assumption that we have two different limits and that they are not equal, that one is larger than the other. Okay? The proof is done, and we conclude the limits are unique. Okay, next thing on our to-do list for today. Left and right-sided limits. Let's introduce these two. So suppose we have a graph, as I've drawn here, f of x, and at the point A there is a problem. The graph happens to have a jump discontinuity. Okay? We cannot talk about the limit as x approaches A of f of x and say that that's equal to one unique value. Which value does f approach as we approach A? Well, on the one side, it approaches L if we happen to have our x's approaching A from the left side. Whereas if our x's approach A from the right side, okay, the values happen to approach something else. They approach M. But if we look at both sides at once, we see that f doesn't tend to any value. Okay? Now, that's a problem, because in the usual limit definition, what we're doing is we're choosing a symmetric delta window around A and saying that, well, we want to make f close to a single number as the x's are coming in around A from both sides, from both directions. Okay? In this particular case, we have to say that the limit does not exist. f doesn't tend to any one value as we approach from two sides. However, we still would like to say something. We still would like to say that if we go from one side, if we approach a from the left side, then we do have a limit, and it is equal to L. Whereas if we approach from the right side, also f does tend to something. It tends to m. So that's where left and right-sided limits come in, okay? How do you define them? Well, let's look at the right-sided limit first. Right-sided limit. How is it denoted, by the way? Limit as x approaches a from the positive side. We're going to put a little plus up over here, up at the a, of f of x. Okay? We denote the limit from the right side like this. We're going to say that this equals m, in this case that we have. Okay. The left-sided limit, denoted in a very similar way, left-sided limit, lim x approaches a from the negative side of f of x. Okay? This one is going to be equal to m. So we're approaching from the positive side or from the negative side. Okay, so how do we formally define these? Well, the right-sided limit, what we want to say is that f can be made very close to m, so less than epsilon away for any positive choice of epsilon, as long as x is pretty close to a, but is larger than a, because we're approaching the a from the right side. Okay, so the definition here is going to look very similar to the usual limit definition, with one minor modification. Okay, so for all epsilon greater than 0, there exists a delta 1 greater than 0. Okay, delta 2 will come into the picture here. There exists a delta 1 greater than 0, such that 0 less than x minus a less than delta 1 implies f of x minus m is less than epsilon. Okay? Where is the difference from the usual limit definition? Here. X minus a is no longer in absolute values. We want the x minus a to be strictly positive and less than delta 1. So we want our x minus a to be strictly positive. That means that the x's are larger than the a's, but not more than delta 1 away from a. Okay? So if we put in our little window here, it will only be on the right side of a. Okay? There's a. This point out here is going to be a plus delta 1, and our x's are going to be chosen from within that little window. They're going to shoot up to the function, and we'll see that the function is approaching m. Okay? So that's the definition of the right-sided limit. The left-sided limit, formal definition, very, very similar. For all epsilon greater than 0, there's a different delta, delta 2 greater than 0, such that, and now we have to modify this to make it a left-sided limit, okay? We want negative delta 2 to be less than x minus a to be less than 0. And that's going to imply that f of x minus L is less than epsilon. Okay? So here, we're told that the x minus a is in fact a negative quantity. Well, that makes sense because x is to the left of a, okay? This is a negative quantity, but it's not too negative, okay? It's larger than the negative delta 2. So if we look at our graph here, we now have a little window over here to the left of a, like that, okay? This part over here is a minus delta 2, and the x's are chosen here, within, or between rather, a minus delta 2 and a, okay? We feed those into the function, and the function is tending towards L. That's what the statement is saying, okay? So very similar definitions to the ones that we're used to, okay? Let's call this definition R, and let's call this one L, okay? Now, we have a very useful theorem, okay, concerning these left and right-handed limits. And the theorem says the following, that if the limit as x approaches a exists, the two-sided limit, and equals some value, then both of these left and right-sided limits also must exist and equal that same value. Let's write that down. Theorem says that the limit as x approaches a of f of x equals some value L, let's put capital L this time, if and only if, actually, it's a two-directional thing, if and only if limit as x approaches a from the negative side of f of x and the limit as x approaches a from the positive side of f of x both exist, and both equal L, this common value. Okay? Useful little result. And here, by the way, we can conclude exactly what I said at the beginning, that the two-sided limit of f of x as x approaches a doesn't exist here, because even though I drew the function in such a way that it appears that both left and right-handed limits exist, they are not both equal. Okay? So therein lies the problem, and we say that this function has a limit which doesn't exist. So let's prove this theorem, and then we'll talk about limits that don't exist a bit later, by the way, okay, in a different video. But let's prove the theorem for now. The proof is going to be pretty straightforward, just manipulating the definitions a little bit. Okay? So this is an if statement, which means we need to go two ways. So let's first assume that the limit as x approaches a of f of x exists and equals L. Okay? So direction one. Suppose that the limit as x approaches a of f of x exists and equals L. Okay? Then what do we know? Then we know the definition, right? Actually, maybe I should put this as a double implication. There we go. Double implication. Then we know the definition, right? We know that for all epsilon greater than 0, there's a delta greater than 0, such that 0 less than x minus a less than delta implies f of x minus L is less than epsilon. Okay? There's our definition. Geez, I forgot to write proof. There we go. All right, proof. So we have our definition of limit. And now we're going to manipulate this a little bit and show that both of these two definitions of limit come out of it. All right? So we know that for all epsilon greater than 0, there's a delta such that this implies this. This absolute value can be expanded. We can take one half of it, the positive half of it, and we can also take the negative half of it. Okay? So this double implies, actually, that for all epsilon greater than 0, there exists a delta greater than 0, such that, on the one hand, 0 less than x minus a less than delta implies f of x minus L is less than epsilon. And on the other hand, 0, or rather negative delta, less than x minus a less than 0 implies f of x minus L is less than epsilon. Okay? So there's a single delta such that this piece implies that, and this piece also implies that. Right? Both of these, when you combine them together, you get that. Okay? Or this splits into these two statements. Now, each of these two statements look a lot like these implications, right? Almost exactly that way. So, what we know now is, well, we can split this single for all epsilon statement, there exists a delta, into two such statements. Okay, so this is true if and only if for all epsilon greater than 0, there exists a delta greater than 0, delta 1, let's say, such that 0 less than x minus a less than delta 1 implies f of x minus L is less than epsilon. The delta 1 in here just happens to be equal to this delta, okay, which we know exists from this statement. And for all epsilon greater than 0, there exists a delta 2 greater than 0, such that negative delta 2 is less than x minus a is less than 0 implies f of x minus L is less than epsilon. Okay, I just split this one statement up, which had two parts at the end to it, into two full epsilon delta statements. Okay, I did choose a separate delta 1 and delta 2 here, but it turns out that they're both equal to the same thing. They're both equal to delta. So, but writing them as delta 1 and delta 2 makes it now very obvious that this is exactly the definition for the right-hand limit, right-sided limit, this one over here. Okay, this is exactly R, and this one is exactly L. Okay? So from the proof, we showed that there exists a delta 1 and a delta 2, both being equal to delta, the delta which happens to work for this statement, which was assumed at the beginning. Okay? So assuming this, we conclude R and L both exist and both equal the same value. Okay? Conclusion, R and L both hold. Okay? There we go. So the two left and right-sided limits exist and are equal to L. Okay? Proof is done. Well, one side of it anyway. But in the way I wrote this, you can pretty much see that the other direction follows as well. Okay? So this was one direction. Let's now go through the other direction. I'm not going to write it down. I'll just explain it because I'm lazy. If we now assume that the right and the left-sided limits exist and are both equal to L, we're assuming these two lines at the bottom here. Okay? And now we can take these two lines and fold them together to make this line over here. Okay? When we're passing from here to this line over here, we want to show that there exists a single delta which works for this implication and also for this implication. Okay? Which single delta do we pick? We let delta equal to the minimum of delta 1 and delta 2. Okay? Since we're assuming these two statements at the bottom now, we are assuming different deltas. However, we can choose a third delta to be the minimum of the two, and now we know that, well, both of these implications will hold when delta is the smaller of the two. Okay? So both of these hold. We can now fold this statement into this one. Okay, this is an if and only if. Since the left side, x is chosen on the left side of a, less than delta, make f of x minus L less than epsilon, and also x is chosen on the, I mixed them up. This was the right side, this was the left side, okay? If both of these implications hold, then we can fold this together and say, well, all the x's within the double-ended delta window around a work to make f of x minus L less than epsilon, and that exactly means that the limit exists, the two-sided limit exists, n equals L, okay? So the theorem is proved. One direction is written for you, the other direction is explained for you. Done. So a useful consequence of the theorem we just proved is its contrapositive. So let's write that down. Contrapositive. So let's reverse this statement over here. This is an if and only if statement. So if this side implies this side, we're going to reverse that and say, well, this side will, not this side is going to imply not that side. Or the converse of that will work as well. Okay? So the contrapositive states the following. That if the limit as x approaches a of f of x does not exist in equal L, so just does not exist, doesn't exist, then what happens? This side is not true. So either one of these limits doesn't exist, or both of them exist but equal different values. Then either limit as x approaches a from the negative side of f of x. Now doesn't exist is written like this in math. DNE, does not exist. Okay, so I'm going to use that abbreviation, so I write less. Then either that limit DNE, or the other limit, x approaches a from the positive of f of x, DNE, or both limits happen to exist but equal different values, or the limit as x approaches a from the negative side of f of x, or, I'll just write, both limits exist but are not equal. Okay? And of course, I wrote this as an if-then statement, but you could write it as an if and only if statement as well. Because this was an if and only if, so when we invert it, when we do the contrapositive, we get another if and only if. Okay? There we go. Why is this useful? We'll see later. I'll make a video in the future which talks about proving that limits don't exist. Okay? And this will be a useful result to know, because if we want to show that some limit doesn't exist of a function, we either have to negate the formal epsilon delta definition and then show that the negation holds, or rather that the formal definition fails, okay? That sometimes could be a little tricky, or the problem is reduced to, looking from either direction anyway. So it is useful to have this result which says that we can handle that, if that's what we want to do, using these left and right-handed limits. We either need to show that one of them doesn't exist, or we show that both of them do exist, and by the way, showing that a limit does exist is probably a bit easier than showing that it doesn't. Or we show that both of the limits do exist, however they equal different values. And that, by the theorem we proved, is equivalent to showing that this limit doesn't exist, okay? So we'll do more examples, some examples anyway, with this in the future, okay? But I just wanted to put it out there, just so you know it a bit ahead of time, okay? What else do we know about left and right-handed limits? Maybe I should state this down here. Left and right-handed limits are unique. I wrote sided before, not handed, so sided. Left and right-sided limits are unique. And the proof is nearly identical to the proof we've just done with two-sided limits being unique at the beginning, okay? Maybe I'll leave that to you. Left to you, although it really isn't very much work at all. You just adapt the other proof which you've seen, okay? The left-sided limit is unique, and also the right-sided limit is unique, okay? And what else do these left and right-sided limits help us with? They help us with proving continuity on an interval, on a closed interval, okay? So let me just quickly talk about how you do this, because this is something we sort of skipped over. In the last video, I talked about how you go about proving a function is continuous on R or on some other open interval, but we haven't really discussed closed intervals, okay? So suppose you want to prove that f of x is continuous on a closed interval. Let's give it a name, a to b, okay? There's our closed interval a to b. Draw a little picture maybe. There's the function. It always looks like this, okay? And let's say we want to prove continuity on a to b. There's a, there's b, okay? We're looking at this segment of the function f, and we want to prove that it's continuous here, okay, on that closed interval. What does it mean? Well, by definition, f is continuous if it's continuous at every point, okay? F is continuous within this interval if we have continuity at every single point, okay? But now, since the interval is closed, we do also have to worry about the endpoints of the interval, okay? So, the method here, the procedure rather, maybe I should write procedure. Procedure is as follows, okay? This is a three-step thing. The first step is to show that f is continuous on the open interval a to b, okay? And what we want to show for that is that for all c inside a to b, the limit as x approaches c of f of x exists and equals f of c, what we want, okay? So that's the first step to showing continuity on a closed interval. We show continuity on the open interval. We disregard the endpoints, and then we show that the regular limit here exists and equals the value it should have, okay? The second step, we want to show that f is right continuous at b, is right continuous, right cont, okay, at b. And what that means is that as you approach b from the right side, oh, I messed this up, didn't I? All right, the function is right continuous at a. As you approach a from the right side, so within the closed interval that we're considering, we are now tending to the endpoint. We want to show that f will have the expected value, that maybe there isn't a hole here that's filled in somewhere else later, okay? F is right continuous at a. That means that the limit as x approaches a from the right side of f of x exists and equals the expected value f of a. Okay? We fill in this endpoint here with the value that it should have. Okay? And the third step, we might as well just guess it, show that f is left continuous, left cont at b. And what that means is that the limit as x approaches b from the negative side of f of x equals f of b. Okay? Same thing, just for the other endpoint. We're approaching b from the left side, and we're showing that the limit, left-sided limit, exists and equals f of b. Okay? That's what left continuous means. So maybe we'll do an example like this in the future, where we show that f is continuous, some function is continuous on some closed interval. Then we'll go through these steps. Okay? But now at least you know them in advance. I think that's it for now. Yeah. Thanks for watching.